So the two things that you guys need to know is the difference between defined point versus limit at a point. Defined point can be shown as an equation like such as this, whereas a limit is seen written as something like this. And now I'm going to present to you guys 3 examples of the difference between a defined point and a limit at a point. Okay, so the first example is the graph of, let's call it f of x, where as at the point f of 1, which is right here, the dotted line, you can tell that at f of 1, the defined point equals 3. In the second example, this is the graph of, let's call it g of x. In this graph, the defined point at f of 1 is 4. However, the limit as x approaches 1 is of the function g of x is actually 3, as you can tell right here. So let's test what you guys know about the difference between a defined point and limit at a point. So for this graph of h of x, what is the limit as x approaches 1 for the function h of x? If you guys said 3, that is correct. The limit as x approaches 1 for the function h of x is 3, as you can see right here, from both the left side and the right side. So the basic theorem that you need to know about limits is that the limit as x approaches c of the function f of x will equal L as long as the limit as x approaches c from the right hand side of the function f of x equals L, and also when the limit of the function f of x as x approaches c from the left hand side also equals L. In other words, this means the limit is defined when the right hand side agrees with the left hand side. So here's an example of a limit that works from the left and right hand side. So what we're trying to do is we're trying to find the limit as x approaches 3 from the left and right hand side of the function f of x. And down here, so we're going to prove the right hand side first. If you can see in the corner right here, there's a positive sign behind the 3. This does not mean it's a positive 3. It means that it's approaching 3 from the right hand side. So what does this mean? So we're looking at everything that goes right here. So let's test it out. The limit as x approaches 3 from the right hand side of the function f of x, as we can see right here, is 2. And down here, we're trying to prove that the limit as x approaches 3 from the left hand side, which is represented by a negative looking symbol, but that doesn't represent a negative, it means from the left hand side, of the function f of x equals And as we can see right here, if we follow it, we can see that it also approaches 2. So according to the limits theorem, this means that the limit as x approaches 3 of the function f of x is defined as 2. But this is not always the case. The limits theorem only works if the limit is defined from the left and right side and they are both equal to each other. But later on you'll see that this is not always the case because there are one-sided limits. Here's an example of a one-sided limit. So let's call this graph the graph of d of x. Now as you can see, the graph in here is different from the one that was just shown because there's a curve that is coming up and then one that is coming down. And so let's try to prove if this graph has a limit from the left and right hand side that equals one another. So the limit as x approaches 5 from the right hand side of the function d of x, as you can see from here, equals 4. And the limit as x approaches 5 from the left hand side of the function d of x equals 0. So the function of d of x when x approaches 5 does not exist. However, if they are only asking you for a one-sided limit, which is either just this alone or this alone, then the limit does exist, depending on which side they ask you for. So now I will go into the 3 types of behaviors that will give you a limit that does not exist. The first behavior is called a behavior that differs from the right and left side. So let's call this graph s of x. When we try to find the limit as x approaches 0 of the function s of x, we can tell that it does not exist because from the right hand side the limit as x approaches 0 is 1, but from the left hand side, as x approaches 0 from the left hand side, the limit is -1. Thus the limit of this function as it approaches 0 does not exist. And we represent that with D and E. So the second type of behavior is called unbounded behavior. Let's call this graph the graph of m of x. And now we're trying to find the limit as x approaches 0 for the function m of x. However, as you can tell from this graph, as it is approaching 0 from the left and right hand side, there is no number that it is approaching. And because of this, the limit as x approaches 0 of m of x does not exist because the behavior is unbounded. So the last behavior is called oscillating behavior. So let's call this function f of x, which equals sine 1 over x. And now we're trying to find the limit as x approaches 0 of the function f of x. As you can see in this graph, as x approaches 0, the graph jumps back and forth from 1 and -1, which means that the limit is differing from 1 and -1, which means this graph does not have a limit. So here's a test problem that you guys can see whether or not you guys learned from this video. So let's try to find the limit as x approaches 0 for the function f of x on this graph. What do you guys get? If you guys said that for this function the limit does not exist You are correct. Because not only is this graph has unbounded behavior, but it also has limits that differ from the left and right.